Thanks, Shahin, for accepting our invitation to talk here today. Shahin is a professor of physics at APM in Tehran, in Iran, and he earned his PhD at the Sharif University of Technology, always in Tehran. After that, he was a postdoc at IPM, then at ICTP in Trieste, and then at ITP at Stanford University, before joining again IPM as an associate professor of physics. Today, he will present the type of cosmology towards beyond the FLRW framework. Shahin, please, you can start when you're ready.
Thank you, Eleonora, and others for putting out this very nice series, CosmoVerse, and for the kind invitation to talk about what we have been doing in recent month, I would say. It's essentially still a work in progress, and we are trying to develop this program in some different ways. Today, I'm going to tell you about our partial results that we have been already published in 3-4 papers. So the work that I'm presenting here is in collaboration with these people that are listed here. So probably unlike the seminars that we have heard recently in this series, this is more like a theory seminar, and I hope I don't bore you with lots of equations. So let me start with some introductory remarks. One should always remember that science and also cosmology in particular progresses through making assumptions and testing them. And this may not be as in cosmology may not be as simple as what we have in other areas of physics, for example. It's not so easy to make experiments or observations, and the quality of the data may not be as good as we want it. And this may mean that verification of some of these assumptions in cosmology may remain out of reach for a long time. And in some cases, some of these assumptions are promoted to the level of principles, and cosmological principle is a very basic assumption in cosmology that everybody is familiar with. But actually, this history of cosmological principle itself has passed through some interesting changes. It started by Copernicus already 3-4 centuries ago, and he put forward the assumption that we are no special observers in space and in time in the universe. There has been constant challenges to this Copernican cosmological principle. Maybe the first one appeared through Olbers already in 1820s, and then was definitely refuted by the observations in early 1920s. The same observations by Hubble and others actually established that we should be using Einstein's general relativity to formulate evolution of the universe, and that has already this program was already started in 1990 by Friedman, and this is basically the main setup for the background cosmology used even today. So the new cosmological principle, the new reading of the cosmological principle can be basically formulated through FLRW cosmologies in the background, which states that the universe around us in constant time slices is homogeneous and isotropic. Observationally, however, this is much harder to establish and test the cosmological principle. As you know, in cosmology, we have background and perturbations, and then perturbations lead to, through the evolution of the universe, leads to different structures at different scales, from few hundred kiloparsecs to gigaparsecs. And then observationally, one may try to define, given all these structures with different distribution over the sky, one may define a cosmological principle statistically or through some coarse graining. So doing so, we always have a scale above which or a precision level below which we can say we have some homogeneity and isotropy. And above, basically, if we are farther than the scale or probing below this precision level, everybody or every object in the universe is supposed to be going or moving with the Hubble flow. And actually, in the last 2 decades, especially the last about a decade or so, the limits of the precision and the scale above which we have this cosmological principle, isotropy and homogeneity, have been pushed back farther and farther. So, and it's going to be pushed in the next decade or so still. And just technically, observation, it's much harder to probe or establish homogeneity or inhomogeneity compared to anisotropy. And just to make the long story short, homogeneity or isotropy are not observationally really established facts, but we know that it's a good assumption to have them. And there are already many different observations or analysis which hint to for some breakdown in isotropy or homogeneity. So I don't want to go through these different observations which hint to this. And you can see our recent review, which we published last year. We have gathered all observational evidence or hints which claim that there may be anisotropy or inhomogeneity in the universe. All in all, it's timely to think about the CPA and its verifications. So just to sort of summarize the introduction, maybe you can keep in mind this figure. Okay. So this is the outline of the talk. I'll try to give one definition or one statement, at least, of the cosmological principle theoretically, and then try to basically argue that what's the minimal deviation of the standard cosmological principle. And this is what we call dipole cosmological principle. And I'll try to formulate this dipole cosmological principle the same way that we have formulated FLRW cosmologies. I'll be focusing on the background in this talk, and I'll try to basically analyze some simple models within this dipole cosmology and tell you about the generic features of these models. And we'll conclude with some remarks and outlook. Okay. So, as a practical definition of cosmological principle, as we are used to today, we basically take a background, spatial homogeneity, and isotropy. This is a practical definition, which leads to FLRW cosmologies, which are basically parameterizing the metric in this way, with this T being the covering time and A is the spatial curvature. So at the theoretical level, isotropy means rotational symmetry over sphere, and homogeneity means that at constant time slices, we have basically the x dependence on the constant time slice of this metric is fixed. So that's what homogeneity means. But in more abstract language, isotropy means existence of three killing vectors which form SO3 algebra, and homogeneity means existence of three commuting killing vectors which form an algebra-like translations. So the cosmological principle theoretically means existence of at least 6 killing vectors. And of course, in cosmology, besides metric, we also have energy momentum tensor of the stuff which fill the universe. And the same cosmological principle tells us that the lead derivative of the energy momentum tensor along these 6 killing vectors must be 0. And this fixes the form of energy momentum tensor in the co-moving frame in the coordinate system that I just showed to be in this way. So that's all what you're familiar with. I just reviewed it because I want to move away from this basic setup. And then basically we have the dynamical equations, which lead to the Einstein equations, which lead to Friedman equations, as you're again all familiar with. And if we have, specify the equation of state of the stuff which fills the universe, we have an autonomous set of equations, and we can try to solve them. And that's all what we do in cosmology, at least at the background level. Okay, so the first steps for moving away from, minimally moving away from this cosmological principle, FRW framework was already appeared in a very nice piece of work by King and Ellis in early 1970s. And basically, it notes the fact that if we sit at a constant time slice in the universe, we may have a non-zero flow of matter at that constant time slice. So, but this could be due to the kinematical effects. So you can be an observer who is moving with respect to the metric, the background metric, or it could be something more genuine and not observer dependent. So this was the basic idea, to consider constant time slices and let there be a non-zero flow of energy momentum tensor through this. So just to visualize it, take this sigma to be a constant time slice, constant t slice in, for example, FRW, the co-moving time. And the flow of matter need not be normal to this surface. It could be along some direction u. And this direction could also be changing in time as you move, or the value of this u, which is this basically the boost parameter, if you wish, could be changing in time. So that's basically the general possibility that one could have. And in the standard FRW cosmology, we have been saying that setting this u to be normal to these constant time slices. So if we have such a non-zero flow, this means that isotropy is broken because we have a preferred direction in the sky. And the minimal setup is that we keep homogeneity, and we basically give up isotropy due to the existence of a vector. And that's what King and Ellis call tilted cosmology. The tilt actually points to this fact that we have a non-zero flow of energy momentum tensor at constant time slices. Okay. So now I want to basically try to formulate or reformulate cosmological principle, which can accommodate some dipoles in the sky. As I already mentioned very briefly, there are some some different hints for existence of a cosmic dipole at cosmological scales at redshifts bigger than 1 from different sources like quasars, supernovae, radio galaxies. And there are also some hints or anomalies in the CMB, which have these anomalies in the CMB have been there since WMAP and continue to be there in Planck as well. I don't want to go to the details of this. I just take them as some motivation. This was at cosmological scales. At much lower scales, few hundred megaparsecs, there is a growing evidence that we may have some non-trivial, non-zero bulk flows. For example, you can see recent papers of Brent Tully. Again, you may see our recent review. So the goal is basically to minimally move away from FRW framework such that we can accommodate the dipole. This breaks isotropy, but we want to keep homogeneity. In this sense, this is sort of maximally Copernican deviation from FRW in the sense that we want to keep the maximum symmetries possible. So the homogeneity, axis symmetry, and local rotation symmetry is basically what goes into this dipole cosmological principle, at least theoretically. Assuming homogeneity, it's very well known that we need to work within Bianchi cosmologies, and they have been classified and known for over a century. And the axis symmetry among these Bianchi models basically lands us onto Bianchi 5 or Bianchi 7. And this was at the level of the metric. And now we want to basically impose existence of 4 Killing vectors, 3 for homogeneity and 1 for axis symmetry over the matter. This basically already tells us that in the standard Bianchi coordinates, T mu nu, the energy momentum tensor, should be only T dependent. So basically the X dependence is dropping out. And then at the level of the energy momentum tensor, we need to add a direction where we have a cosmic flow and the value of the cosmic flow, which we parameterize it through this beta. So let me put these together. So to start with, the answers for the metric that we need to take is a Bianchi 5. It has 2 parameters, one overall scale factor, A, and an anisotropy factor, which is basically related to the cosmic shear. And A naught is a constant parameter here. And of course, we can define the usual Hubble parameter and the shear through the derivatives of this A and B. The energy momentum tensor with this setup that I just mentioned takes this form. It has a usual isotropic part, which is just the standard diagonal minus rho P, and a tilted part, which has this form. And of course, this off-diagonal terms here is basically related to the existence of the flow. And there are some interesting features to note here. For example, if rho plus P is 0, like what we have for a cosmological constant, beta drops out of this whole setup. And also note that here, if due to the existence of this A naught factor here, positive and negative values for the Z coordinate, the Z direction is basically where the flow is along the flow. We have taken the flow to be along the Z direction. And existence of this term basically tells us that parity is broken along this Z direction. So it's meaningful to talk about whether we are moving along the this positive Z values or along negative towards negative Z values. This means that the sign of beta has is physically significant. Okay, and we'll come back to this later. Regarding the dynamics in this dipole cosmology, we have the answers for the metric. We have energy momentum tensor and its form. We have 5 dynamical objects, Hubble parameter, shear, energy density, pressure, and the tilt. And we can use Einstein equations to basically govern the dynamics of the system. And again, as before, we need to supplement the system with an equation of state to have enough number of equations to solve. Doing so, basically, we arrive at what replaces Friedman equations in this type of cosmology set. So this should be familiar. Let me just go through a couple of them. So this equation is basically telling us how the Hubble's and the shear are related to the matter. And as you can see, there appears this tilt on the right-hand side. And this tilt term is always positive definite due to the null energy condition, which implies rho plus p is positive. As for the shear, sigma, it's again related to rho plus p times just sine hyperbolic 2 beta, essentially. This right-hand side is positive. If beta is positive and is negative, if beta is negative, so sigma essentially has the same sign as beta. And as you can see, beta is sourcing sigma. This is a feature of this dynamical equations. Then we have the continuity equations, which are the right-hand side are the usual form, and the left-hand side, the right-hand side receives some contribution from the tilt, and the left-hand sides are just the standard ones. And we want to analyze these equations and basically see how the existence of beta changes the evolution in this cosmology. I already told you that the sign of beta and sigma are the same. And if beta is 0, sigma is also 0. Okay, so let me go through the first example just to give you an idea how the system works. Let's take a simple equation of state, a single fluid with P equals W times rho. And for this case, equations simplify a bit, and one can integrate already 2 of the equations and get these 4 equations for 4 unknowns, H, beta, rho, and sigma. Okay. So basically, let's focus on this equation, for example. If beta is positive, this expression here is positive always because W is between -1 and 1. And as this equation also shows, and one can see it more closely, sigma, which is the shear, actually damps off very quickly. This other term, the last term, is also damping off very quickly because of the appearance of the scale factor here. So essentially at late times, this equation, the right-hand side of this equation is given by 3W minus 1. Hence, if 3W minus 1 is bigger than 0, beta dot is positive. This means that the tilt can grow. So this is one outcome. The other outcome is whether you may ask whether this appearance of the tilt, how does it change the acceleration? And you can see that this term is negative compared to the lambda term. So essentially it contributes negatively to the acceleration, as you can see from this equation. And but then as we'll see, this rho term is basically damping off as we expect. For example, the dust and radiation, they fall off very quickly. And hence the dominant term at late times is still given by this cosmological constant. Okay, so these are just interesting features that there are essentially the acceleration and the dependence of energy density on beta is sort of is not very significant, is not very basically we essentially see the same features as in standard FLRW cosmology, but the point is that beta can grow, at least for the cases where W is bigger than a third. There are other interesting remarks and features that one can see here, but I'll just skip through them to tell you more about other interesting stuff. This I already told you. The important feature that actually is very remarkable is that if we start with positive but very small beta for W bigger than a third, it can grow indefinitely in time if we basically evolve a system far in future. This means that FLRW cosmologies are unstable with respect to turning on this beta perturbation. This is very important, and I'll come back to this in a bit. So we have tried to analyze dynamics of the system numerically with various different values for the initial values of the parameters. And this is one typical evolution that you can see here in these plots. Different colors are associated with different equations of state. And as I just mentioned, for W bigger than a third, for example, here, tilt can grow. And again, shear is usually going down very fast, as we expect. This was for beta positive, but for beta negative, actually, the tilt growth can happen in a wider range of parameters. In particular, let's note that for when beta is negative, remember that sigma and beta have the same sign. So this term could be positive. This term could also be positive. So then we have some more sources for beta. And actually, when W is equal to a third, which is very interesting case of radiation, these two terms are positive, and this can lead to a growth in the tilt. Okay. Let me put it in more physical terms. This means that for negative beta, which is basically half of the choices that we have for the initial conditions, there is a tilt in the radiation sector in the CMB, and it can grow in time. And you should view this as an instability in the standard FLRW cosmology. No matter how small beta, but negative value you start with in the early universe, as the universe evolves within this setup, the tilt can grow. Besides the observational consequences, this tells us that there is an instability in the FLRW setup. So this means that one should actually expect, theoretically, one should expect that there is a non-zero dipole element, non-kinematical dipole element in the CMB. So this is actually, again, let me emphasize, this is regardless of basically whether we have this dipole cosmology or not. Since there is an instability in the FLRW setup, and this dipole cosmology is actually revealing this instability. So one expectation is that there should be some dipole factor, non-kinematical dipole factor in the CMB. This is just theoretical fact. Okay. And again, the fact that the signs of these two terms could be positive, this means that they can source beta, and beta growth can happen even if W is less than a third, for at least some epoch in the evolution of the universe. And we have checked this numerically, that for this, at least there exists some set of initial conditions that for any W, due to presence of these two positive terms, we can have a tilt growth for any W. Okay, so these are again some typical evolution examples that you can see the shear sigma always goes to falls off very fast. Typically, the energy density falls again with some power of A, and beta can grow actually. This is for W equals a third for radiation. Okay, there are many different examples that you can see in this paper. So this was basically a simple example to show you some features of this. In order to do more realistic cosmological model building, we need to basically consider cases where we have some different non-interacting, the simplest cases, fluids, each of them coming with some WI, some equations state. And in order to have a consistent dynamics, we need to associate a different tilt to each of these different components. So we need to add beta I for each component. So these are the dynamical parameters of this generic simple multi-fluid model. Okay, so let me give you one example of probably of special interest, the dipole Lambda CDM cosmology, which we have two component W equals 0 and a third fluid, and we also have lambda. The system has 6 dynamical parameters for radiation and matter and shear and Hubble parameter. Again, one can go through the equations, and as we have done in our recent paper, you can see the details. But here I just give you a summary of the results. So if beta m, the tilt for the matter is tilt for the matter actually always damps down, but beta r can grow, as I just showed in the case of single fluid for the radiation. So as a generic feature of this dipole Lambda CDM model, there is a sizable relative dipole or relative tilt between matter and radiation sectors. So if you, for example, choose to work in a CMB frame where the dipole in the CMB is set to 0, that's what we almost always do, then the dipole or the tilt appears in the matter sector. Or if you basically move, you are in the rest frame of the matter, then you would expect to see the dipole in the radiation sector. What is actually physical observable is the relative tilt or dipole, which is basically sort of the difference between beta R and beta M, and that can grow. And again, generically, shear goes down like A to -3 as in the usual FLRW. Here I basically show you one typical example of the evolution of the system. Here I've taken beta M and beta R to be both negative, and the left-hand side here is basically close to the Big Bang, where the scale factor A is very small, and the time evolves towards the right. And here the right-hand side is now T equals 0, basically. So as you can see, the tilt can grow. This is in the radiation sector. For the matter sector, the tilt actually grows for some time in the past, and then it comes back and basically goes to 0 for today. The shear actually, it's an interesting feature of this, and I would say generic feature of this dipole cosmologies. The shear actually starts from its maximum value, which is here I've taken -3, as you can, let me just remind you. Sorry. From this equation, this term sigma square should be always less than 9h squared, because all the other terms are positive difference. So sigma over h is between -3 and 3 always. So sigma being -3 is saturating its bound. But then it very rapidly goes to 0 and reaches 0, as you can see. Then the other dynamical parameters of interest are rho m times a to power q, which in standard FRW, we expect this to be constant, rho r times a to the 4. Again, we expect it to be constant, which is essentially what we see here. And the shear is dropping with a to minus 3. Again, this is what you can see here. Maybe this right plot is a more interesting one. So these are taken with the Planck values that we have almost here, except for this omega sigma, which we have taken to be much smaller than 1. So as you can see, the universe starts from a shear-dominated era. It goes through a radiation-dominated, matter-dominated, and then it is becoming dark energy dominated. So this is the expected one. Perhaps the only difference with the standard cosmology is that we have an early universe which is dominated by shear. So let me summarize. As you can see, the metric is actually remaining the same. The standard evolution is essentially remaining the same, except for sometime in the past. But we can have a non-zero sizable relative tilt between matter and radiation. And this is actually a sort of generic picture, regardless of the details of the initial conditions. Okay, so let me summarize. There are various hints, of course, yet to be substantiated, observational hints for breakdown of homogeneity and or isotropy at cosmic scales. Maybe among them, the most significant is a dipole anisotropy, which has been reported in some different data sets. The analysis that we have done here, and actually my personal motivation to start thinking about dipole cosmology was coming from this usual H0 tension, and the fact that we have tried many different resolutions and none of them seem to satisfactorily work. And maybe one can entertain the idea that the basic setup, namely the standard FRW cosmology, is not the right one to basically start with. So this was my personal motivation. Maybe that motivation is not so strong as we started 2-3 years ago, but it's interesting to keep this in mind, that if the universe is not FRW for whatever reason, one needs to revisit H0 and SA tensions and all the other anomalies in the standard model. Okay, I've tried to present and formulate the dipole cosmological principle. And basically, as a generic feature in these models, I showed that the shear, which parameterizes the anisotropy, goes to 0 at late times, but the tilt can grow. And this is, of course, for those of you who have more theoretical interests, this is compatible with the Wald's cosmic Noether theorem, but is a refinement of that when we consider the tilt, actually. And we also showed that the relative dipole or relative tilt between matter and radiation can grow in time. And importantly, FRW cosmology is unstable against tilt perturbations. So theoretically, one should expect to see, not to see actually FRW cosmology. This is sort of, I think, very important to keep in mind. And we are now trying to develop further the dipole Lambda CDM model, the observational consequences of within this model, and whether this could be related to the dipole observations that have been reported in the literature. So that's what we are trying to do. now, and I hope we can publish it in a few months. So I'll leave you with my last slide. Thank you.
Thank you so much. Yeah, Osgur has a question.
Hello, Shahin.
Hi.
Thanks a lot for the very nice talk and bringing this subject, which has been overlooked in the last 2 decades. So I would like to ask a couple of things. Okay. So first of all, I mean, I know you in your previous papers you are talking about tilt cosmologies. Now I see you're also talking about shear scalar. So because you are using Bianchi type 5.
Mm-hmm.
So you have, then there should be quadrupole also, not dipole, right?
Okay.
I mean, so for that reason, first of all, but this shear scalar behaves like a to the shear scalar sigma squared behaves like a to the minus 6, like a stiff field. So and we have cosmic no hair theorem.
Mm-hmm.
Right, then so how could shear scalar have been survived from inflation? So if these are true, I mean, so I mean the inflation shouldn't be realized by scalar fields, right? I mean, so should we go for vector fields?
No, actually the point is shear is something defined at the level of metric, and metric could be isotropic, but still we can have non-zero beta. Beta is associated with the matter that we have.
Yeah, I'm okay with beta. I know tilt can survive from inflation, but shear scalar, according to cosmic no hair theorem,
yes, it goes to
you
zero.
don't expect, right?
Yes, and actually, typically, I'm showing one example here.
Yes.
So even if you start with the maximal value for the shear at the very early times, the evolution basically damps it very fast.
So,
right? This is what we can see. This is sigma over h.
yeah, well, so I would expect it to dominate the early universe. So,
Yes, it does actually.
yeah. So that is another point. I mean, so I think your analysis from Planck is at the background level, right?
Sure, of course.
So,
everything in this talk was
we have one paper recently published, constraint anisotropy, but Bianchi type 1 also we constrain. So the point is this, I mean, in CMB power spectrum, if we use full data analysis, at the background level, the constraint is like 10 to the minus 13. But if we consider full temperature anisotropy, it should be like 10 to the minus 21 because on the shear scalar. So to overcome this problem, there is one method. We may consider, I mean, if we want to shear scalar live in the late universe, maybe we should go for anisotropic dark energy models. Otherwise, CMB power spectrum will not allow us to have omega sigma larger than 10 to the minus 21. And one more thing, and the BBM constraints on shear scalar is like 10 to the minus 23. You see, it dominates before BBM, so this will spoil the BBM. So, and all these may be solved simply by describing dark energy with an anisotropic pressure, like vector fields or anisotropic pressure. So, I mean, if you'll get something from this, would you think of considering anisotropic dark energy models in this case?
Okay, so as I said, this is just a minimal setup that we have analyzed, and there is a lot to be done here. So I just showed you some very basic models. What you're telling about anisotropic dark energy, probably you mean for the late universe.
Yes, but my point is this. I mean, if you have either a source in general relativity, if you have isotropic source, then shear scalar will behave like stiff fluid. For that reason, it is very dangerous. It spoils everything in the early universe. But if you have anisotropic source, I mean, a source with anisotropic pressure, then we can control behavior of shear scalar. We can even make it constant. So in that case, we can have large anisotropies in the late universe. To do that, what we need to do is to allow dark energy source to have anisotropic equation of state parameter. We can discuss this later on, but
let me emphasize that what you're saying is interesting, but there are two remarks. First of all, tilted cosmologies cannot happen for Bianchi type 1 models. Okay. This is what King and Ellis have done in their paper of 1973. So they basically they have shown which Bianchi models allow for having a non-zero tilt. Bianchi 1 is not a model.
No, yes, but
so this,
Bianchi 5.
I'm just making some theoretical remarks. The second thing is that basically, if you want to have a dark energy, which is roughly the same parameterized by a cosmological constant, Wald's cosmic no-hair theorem is basically telling you that shear goes to zero very fast, essentially like a to -3, and scale factor is itself going like exponentially fast with the Hubble parameter, right? So basically, I don't think that in any realistic cosmological model at late times, shear is going to play any role or will have any observable feature at late time. But nonetheless, beta, the tilt can be sizable. It's not, so basically the point is, most of or almost all of our observations is not about the background metric itself. Is about the distribution of, for example, radiation or matter that we have in the universe. So trying to attribute everything to the metric is maybe not the most interesting model building setup to start.
Okay.
So.
And one last comment. I'm sorry, I talk a lot, but also you are using Bianchi 5 metric. Can I see the metric?
Sure. So
I think this is the locally rotational symmetric Bianchi type 1 metric, right? I mean,
there is this power
yeah, because
-2.
Yeah, the x and y axis have the same scale factor, right? So my point is because I mean there is this is not the most general Bianchi type 1 metric.
It is not Bianchi 1. It's Bianchi.
Sorry, 5. Bianchi, not the most general one. So you can have 3 scale factors. Then in that case, you can even allow model to have 8 flux. You have one more equation. You set it to 0 from by hand.
Yes, we set it to 0 because we want to be maximally Copernican. We want to basically keep as much symmetry as possible and still allow for a dipole. Of course, one can deviate from this. That could be done. Okay. So we are trying to consider the simplest cases.
Okay, thank you.
Let's thank Shahin again.
Thank you for having me. Thank you for